Hey, welcome to our discussion on understanding velocity graphs. Today we're going to review the slope of a distance versus time graph, and also we're going to cover what the velocity versus time graph, what its slope means. And then at the very end we're going to start talking about the area under a graph, and that's a new concept. Let's get started. So you'll recall from previous conversation that the slope of a distance versus time graph is the velocity of the object, and we got that of course by saying, hey, slope is equal to the rise over run. The rise, of course, is distance here, and the run is time. And we said, hey, distance divided by time, that is equal to velocity. We even confirmed that by looking at the units, and we said, okay, so meters here divided by seconds, and if I get units of meters per second, that is also velocity. So we had two ways of verifying that we had something meaningful. So it's kind of weird that the angle of this line, so the steepness of this line, that number tells you the speed of the object. But it's a neat trick. So slope here is equal to distance versus time. Let's do that same thing, but let's look at it from the perspective of the velocity versus time graph. So again, we have to remember that slope is equal to rise over run. But in this case, instead of the rise being distance up here, it's velocity. And we say the rise is velocity, and the run is still time. Now, is this meaningful is the question we have to ask ourselves. Velocity divided by time. So this is how fast I speed up or slow down, my change in velocity over change in time. And that is acceleration. So the slope of a velocity versus time graph tells you how fast your velocity is changing, just like the slope of distance time graph shows you how fast your distance was changing. We call this one velocity, and we call this slope acceleration. Sounds good so far. And now let's verify it with the units. So if we take the units of meters per second and divide by second, we get meters per second per second. So this tells us how many meters per second we speed up every second, and that maps back to acceleration. So we got something new here. So the slope of velocity versus time graph is equal to the acceleration of the object, how fast it's speeding up and slowing down. Before we move on, let's quickly take a look at a few ideas on the graphs. So here, our velocity is constant, it's a straight line. And if our velocity is constant, we're not speeding up or slowing down or turning. And we'll remember that the three ways we can accelerate is by speeding up, slowing down, or turning. And on this graph, we're not doing any of those. We're staying at constant velocity, so our acceleration should be 0. And sure enough, the slope here is 0. And then at this point, we suddenly slow down. Really quickly, we slow down to a new, slower speed. And we have this huge negative acceleration, this slowing down happening on a very steep line here. And then another 0 acceleration here as we stay at constant velocity. 0 acceleration, 0 acceleration. All these are constant velocities. So far, so good. So that's the slope of a velocity versus time graph. Okay, let's take a look at an example here real quick. You'll notice here in this example on our distance time graph, we start off with not much slope, so 0 velocity, really slow. And then we speed up, speed up, speed up, speed up, speed up. And we could take the time to calculate this, but let's say this is a really fast velocity, like 15 meters per second. We're always positive. So our velocity versus time graph is going to start at 0, and it's going to end up here somewhere really fast, let's say 15 meters per second. Okay? And if we had done this math, we'd find that this was pretty close to 15 meters per second near the top here. Now, once we do that, if we want to know our acceleration, remember that slope of a velocity time graph is equal to the acceleration. So if we find our slope, we'd use our velocity here. Our velocity went from 0 all the way up to 15 meters per second. So that's 15 meters per second divided by, and that took us, this from here to here is 6 seconds. And we said from here to here was a change in velocity of 15 meters per second. So we do 15 meters per second divided by 6 seconds. And that's our acceleration. That's how much time it took to speed up. If we do this math, we get 2.5-ish. Now the units here are meters per second per second. So that means that every second we speed up by 2.5 meters per second. And if we do that, in 6 seconds, we'll have a speed of 15 meters per second. Awesome. So now we've learned some really powerful tools for using graphs, distance versus time and velocity versus time graph. Our first rule was that distance versus time graphs are equal to velocity. And then we just learned today that a velocity versus time graph, the slope is equal to acceleration. So we have these different meanings for the slope of the different graphs. Now we're going to look at a whole new way of getting information from a graph. So one of the ways we get information is from the slope. The other is from the area under the graph. Of course, to find the area of something, we multiply instead of divide. The slope is dividing, the area is multiplying. So in order to figure out if the area is meaningful, we simply multiply y times x, and if that is meaningful, then what we have is meaningful. So let's take a look. If we take distance and we multiply by time, so here the area of a distance versus time graph is equal to distance times time. And that would be meters times seconds. And in this case, meters times seconds is not a meaningful unit. There's nothing that really means that. So for distance versus time, area is out. It is not meaningful. And it's one of the reasons you've never seen the area calculation before, or you may not have seen it, is because it's really not useful on a distance time graph, which is one of the most common graphs to make. Let's do that same analysis on the velocity time graph, see if it's meaningful. So again, area is going to equal to x times y, which is equal to velocity times time. So that's velocity times time. And if you multiply velocity times time, the units would be meters per second times seconds. In this case, seconds would cancel out, and you'd end up with just meters. And we know that if we multiply our velocity times our time, that gives us a distance. How far we traveled. So the area under a velocity time graph is meaningful. The area is equal to distance. And really it's equal to the change in distance. Let's take a look here. So in the first 2 seconds, from our distance time graph, we can see we went from 0 up to 10 meters. So if we find the area in the first 2 seconds under the curve, that's between 0 and the line, here's that area right here. I'll box it in. If we find this area, let's do it real quick. This side of the box, it's a rectangle, so it's going to be, length times width. This part is 5 meters per second. This part is from 0 to 2 seconds, so that's 2 seconds. And 5 meters per second times 2 seconds is equal to 10 meters. And sure enough, the area inside this box matches the distance we know we traveled. Now the area inside this next box is going to be 2 meters per second, high here, times 2 seconds for a distance of 4 meters. And sure enough, during this part, we went from 10 to 14, which is a 4-meter change. Altogether so far, if we count all this together, we're looking at 14 meters traveled, and sure enough, at 4 seconds, 14 meters. So we have this very weird thing that somehow the area under the curve matches up with the distance traveled. Now, there's no reason for that. There's no special connection between the two. It just works out that way when you put velocity on this axis and time on this axis. Just like when you put slope, when you do the slope, it becomes acceleration just because that's the way we set the graph up. It just works out great that way. It's one of the reasons these graphs are so awesome. Now this last little bit, this last area here, if we calculate it, this is negative 14 meters per second. This is 1 second. So the area here is negative 14 meters. That times that. And we see that we have all this together as positive 14 meters plus negative 14 meters gives us a total distance change of 0 And sure enough, we're back here at 0 at the end of the graph. So that's kind of cool. The area of the graph is meaningful for a velocity time graph, and its meaning is distance. It's how far something's traveled. Let's look at a few examples real quick. So I've created different velocity versus time graphs to help see how to calculate area of these graphs. So in this first graph, we calculate area of this first box. Calculate that area, and then we'll calculate this area. And now notice there's no space between the line and 0, so there's no area here. We're going at 0 velocity, so we're not traveling a distance, so there is no distance to add to it. And then finally, we'll do the calculation of this box here. So in this first box, this side of the box goes from 0 to 5 meters per second. This side goes from 0 to 1 second for a total change of 1 second. And 5 meters per second times 1 second is 5 meters. In the next one, we go from 0 to 15, so this side of the box is 15 meters per second. This side of the box goes from 1 to 4 for a total of 3 seconds. And 3 meters per second times 3 seconds is an area of 45 meters. So far in the first 4 seconds, we've gone 45 plus 5, a total of 50 meters in the first 4 seconds. And then this last one, we're going, this side is 10 meters per second. This side is 1 second. So we end up with 10 meters. And here we're going 0 meters. There is no area underneath that curve, or between the curve and the 0. So in total during this trip, during the 6 seconds, we went 5 plus 45 is 50 plus 10 is 60. We went 60 meters in those 6 seconds. Awesome. Now this next one, we need to find the area under the curve, so the area of this triangle right here. We have to calculate that area. We've got to then calculate this area. And then finally we have to calculate this last area, which is this triangle. We'll do those 3 things separately and add them together to find the total distance traveled. Let's start with this first triangle here. We know that the area of a triangle is 1/2 base times height. So in this case, here's our base, here's our height. Our base starts at 0 and goes 2 seconds. Our height starts at 0 and goes up to 15 meters per second. 15 meters per second. Our base times height times 1/2, so 2 times 15 is 30, times 1/2 is 15 meters. So in this first section, where I'm accelerating, I'm speeding up, I'm going only 15 meters during that time. Now in the next segment, I'm still got 15 meters per second, and I'm doing a rectangle at this point. So now this is just going to be length times width. So 15 meters per second times from 2 to 5, that's 3 seconds. So that's a total of 45 meters. Now in this last one, it's going to again be a triangle. So it's 1/2 base times height. So the base goes from 5 to 6, 1 second base. The height here again is 15 meters per second. And 15 meters per second times 1 second times 1/2 is 7.5 meters. Good. Now we have our three distances. We just add them up to find the total distance. 15 plus 45 is 60 meters, plus 7.5 is 67.5 meters total on all 3 of those. All right, that's our final example. I hope you learned a little bit something new about the area of a graph, and especially with velocity time graph, the area is the distance.